Hello and welcome to Section 8, I-equivalence. To recap, we found that there are a number of minimal I maps according to which the joint distribution of the variables of interest can be factorized so that the resultant factorization matches the data set. Like here we had two candidates, both of them are minimally I map. In this one, it's linking from C to M, D being completely isolated, and same with the other one here, just that the link is from M to C. Now the question is there a class of minimal I maps? Well, we haven't defined what we mean by a class, but we have a sense of a similar property that holds among all these minimal I maps. And I'm going to explain that here. Using the Bayes rule, three types of structures have equal distributions. We have seen this before. So if I have the three variables x, y, z, the joint distribution can be written in this way, can be factorized according to the ordering x, y, z, and the corresponding graph will look like this. Now, using the Bayes rule, I can just sweep the place of x and z so that instead of p of x times p of z given x, I can write down p of z times p of x given z. And the resulting graph will then look like a common cause. Still, these two have the same identical joint probability distribution, and I can also reverse the direction in this other way. For all three graphs, I have the same probability distribution, the joint probability distribution, which implies that in all of them, I have the same global set of independencies. You can easily check that in all these three, x is independent of y given z. Like when z is known, the trail from x to y is blocked, and they become independent. So distribution-wise, the three are indistinguishable. However, the same would not hold if we had the set of independencies being limited to x independent of y. Then the graph would take a V structure. Here, x and y, they are independent and they should be linked to z. You may say, well, why don't I just make all three independent? Because then that graph imposes some additional independencies such as x will also be independent of z given y, which is not included here. We had a discussion on this in the previous sections. Okay, so the corresponding graph for this set of independencies, global maps, global I map, is this V structure, and correspondingly the distribution can be written in this way. P of z condition on x and y times p of x times p of y. This cannot be converted to another structure by using the Bayes rule, which is clear because if it was possible, then the IG of this would be equal to one of these ones here, this one, which is impossible. So V structure is not equivalent to the previous three structures. And here we go with the so-called independence equivalence or I-equivalence. Two graphs G1 and G2 defined over the same variables are I-equivalent if the set of their global independencies match. I of G1 equals to I of G2. Now, we can drive a proposition, it's not difficult to prove it, that if two graphs have the same skeleton, meaning that just ignoring the directions, the structure of the graphs are the same, and they have the same set of V structures, then they are I-equivalent. So if I have two graphs with the same skeleton and also the same V structures, then their IGs will match. Okay. Now let's see an example and also how we can prove such a thing. So in this example, we're given two graphs G1 and G2, and we're asked to prove that they are I-equivalent. How can we do that? Well, using the proposition, it should be straightforward, right? they have the same skeleton and the same V structures. The skeletons are the same, yes. And this one has only one V structure, X, Y, Z, and so does this one. So by the proposition, they should match. But how can we prove it in this case? Okay, here's the idea. Let P be a distribution for which G2 is a P map, meaning that IP matches IG2. So I'm looking at this graph. I'm constructing a P, considering a P distribution for all the variables so that the independencies are exactly the same as those imposed by G2. Now, I can write down the joint distribution of this graph and factorize it according to G2 in this way. It's just P of V condition on W, W condition on X, here we go, and I have P of X, it has no parents, and P of Y condition on both X and Z, and then finally P of Z, based on the factorization of Bayesian networks. Now these blue ones, I can use the Bayes rule and switch. So I can write down this part as P of W times P of X condition on W. Okay, that is basically equivalent to reversing the direction of this link. And then I can take a look at this part and write it down equivalently as P of V times P of W condition on V. So that means that then I'm reversing the direction of this one. And this is exactly the same as G1. So this distribution P that I considered here does factorize according to G1 as well. This means that I of G1 is a subset of IP because we just saw that P factorizes according to G1. It may have additional independencies, but it certainly holds that IG1 is a subset of IP. We don't know if it's a P map for G1 yet. But then we know that IP equals to IG2 because we consider it to be a P map. So IG1 is a subset of IG2 or equal to, and it can similarly be shown that IG2 is a subset or equal to IG1. So the two of them will yield IG1 being equal to IG2. Now you could also use d-separation to just show all the independencies that are included in G1 are also included in G2, and to show that the two are I-equivalent. Okay, so we showed that these two are I-equivalent. Their I's, the global I maps, are the same. Now, in general, the arrows in a trail can be reversed as long as a new V structure is not produced. So, for example, if we have a trail like this, and we have Y linked to Z linked to X, the joint distribution will be the multiplication of the CPDs, each node condition on its parents, all of these nodes here, and when we get to here, it will be P of X condition on Z and P of Z condition on Y times P of Y in this case, if Y does not have any incoming nodes, any incoming links. And then again, Bayes rule, well, we can reverse the order like this, right? So this part, I can write it in this way. So these two will have identical joint distributions. And this was also evident here. Like you see, I'm not touching the V structure, but I'm switching the directions of these links here, which are not a V structure. Like here I have X, W, V, and here I have V, W, X. Or I could make them common cause. Still, it wouldn't make a difference. So that's what we're showing here. G1, G2, G3 are I-equivalent. You see the V structures are the same. Here I have XWV, VWX, and a common cause W going to V and X. Okay? And what I can further conclude is that no other graph is I-equivalent to them. Okay? We so far have only shown the sufficient condition for being I-equivalent, not the necessary. We will get there, but you can just see that at least according to the proposition, If I change the direction of any of these, then I no longer have the same V structure. And if I change the direction of VWX so that it doesn't fall into these three graphs, then I will have VWX to W, which means that I'm creating a new V structure. And then it doesn't fall into the proposition anymore. So then the question is, do any two I-equivalent have the same skeleton and V structure so that I can extend the proposition to a necessary and sufficient condition? And the answer is no. Here's an example. Consider the three random variables x, y, z so that there is no conditional independence imposed on them, I of g equal to empty. Then I can have one of these six possibilities. Recall that if a graph is completely connected, then there's no conditional independence imposed by the graph. This is the situation here. So for example, in this one, x is connected to both of the nodes, so it cannot be independent of them using d-separation, regardless of what we are conditioning on. And the same story with all other graphs. So the joint probability distribution of all these six are the same. We are writing them in different forms, but they are independence-wise equivalent. And the reason is because we are using the chain rule. So here, for example, P of x times P of y condition on x, this is basically P of x and y, and then multiplied in this, we will get back to the original distribution. And the same with all other ones. So here we see that although we have the V structures that are different in these six graphs, still they are equivalent. So what is going on? Before answering the question, just a little exercise. There are in general 8 different DAGs with the vertices x, y, z. Why do we only have 6 here? I will give a hint or almost the answer. Well, 2 of the cases will result in a cycle, whereas a DAG is an acyclic graph. Okay, back to our observation. All 6 graphs are I-equivalent, but don't share the same V structures. This is because the parents in the V structures are linked. Okay, let's go back here. So yes, I do have Z being a V structure, X to Z, Y to Z, they're both connected. So I will have the terms P of Z condition on X and Y, but the point is that here I don't have P of X times P of Y, I have P of X times P of Y condition on X. And this allows me to write the multiplication as P of X and Y, and then multiply by this, I will get back to the original joint distribution. So this link is really helping out here. And that is what we call that they are moral. There is a link between them. So back to our original question, do any two I-equivalent have the same skeleton and V structure? No, only the immoral V structures should match. So what do we mean by morality and immorality? Well, if we have a V structure where X and Y are not connected to each other, we say that we have an immorality. If there is one, then we say that we have a morality. And in this case, this red edge connecting X and Y, it's a covering edge. So that's the definition for a V structure being an immorality and the definition for covering edge. Now here's the concluding theorem. The graphs G1 and G2 are I-equivalent if and only if they have the same skeleton, no question on that, you cannot have different skeletons, and same set of immoralities. Once you have that, then we're done. So we should only look for this, V structures where the parents are not connected. These ones are fine. So in this situation, you can change the directions. Doesn't matter, but here you cannot. Let's see it in practice. Back to our COVID problem. We saw that this graph is an I-map for P. It is not the only I-map. It is a minimal I-map. Is it the only minimal I-map for P? And the answer is no. For example, if I just reverse the direction of season to flu, and I make it flu to season, then I'm not causing any new immorality. So here it is not a V structure. There's no V structure here. And by changing the direction, I'm not causing a V structure without a covering edge. I'm not even causing any V structure. And the skeleton is the same. So you see how quickly I can say that there are other graphs with the same distribution. It wasn't that easy here when we asked the same question almost. Is it the only I map? Okay. Now, we can define a class of I-equivalence. The set of all I-equivalent graphs results in a class which can be encoded using a partially directed acyclic graph, a PDAG. In our example of G1, G2, G3, the equivalent PDAG would look like this. So how would we define it? Well, recall that the immoralities are the key, so we keep those arrows present, and the other ones, we just remove the arrows. A class PDAG of a DAG G is a PDAG that has the same skeleton and includes a directed edge only if all of the I-equivalent graphs to G also have that directed edge. So here, for example, we see that V to W can change, like here. It's changing. So here, we don't keep the direction. And so is W to X. However, this is an immorality. It should be the same, so here we keep it. This is the so-called a class PDAG of any of these graphs. How to obtain the class PDAG of a DAG G? How can we get here? Well, it follows the theorem. First, we need to obtain the skeleton, and then we find the immoralities in G and draw them in the skeleton. They cannot change the direction, but then what about these blue ones, the ones without directions? Should we just always leave them any directions they can take? No. For example, obviously, I will first say this one, they cannot create a directed cycle. The DAG should always be an acyclic graph. That is rule 2. Rule 1 is that they do not create extra immorality. So here, for example, I cannot connect X to W and V to W at the same time, because then I'm creating a new immorality and then they no longer satisfy the condition of the theorem. So any other ordering, it's fine, as long as they satisfy these two rules. An example. What is the class PDAG for these 6 graphs that we saw earlier? Well, first I need to construct the structure, and then do I have any immoralities? No. So the answer is simple, just a partially directed acyclic graph in this case where all of the nodes are connected to each other. Another example. Imagine that we start with this graph. The original DAG is given. I want to obtain the class PDAG. First step, I need to obtain the structure. So the structure is just the one with the same network, but where the directions are removed. That's not difficult to obtain, but I have one obvious immorality, BEC here. It is an immorality, so I will keep it in the new graph, right? So this is the immorality. We keep it here in the new graph. And I don't have any other immorality. I should first find a V structure. The only V structure in addition to this is here, EF, CF, but it's not an immorality. We have a covering edge. Okay, what's next? So I can make a conclusion about the arrows here. So for example, can I say A to B or B to A? Will that cause a new immorality? Well, neither of them will cause a new immorality here because A to B together with B to E, for example, will not cause a V structure. On the other hand, neither B to D, the same story here, D to B or B to D will not cause a new immorality. So I cannot decide on the direction. So I will leave them undirected. Now, does this mean that any combination of the arrows here is possible? No, because for example, A to B and D to B, that will cause a new V structure, and actually it's immoral because we don't have A to D connected. What about these ones here? What can I conclude? Well, regarding E and F here, I cannot have F connected to E. Why? Because then I will have a V structure BEF, which is actually immoral. So I should definitely have E connected to F, like here. Now, what about C to F? So if I have this C to E, E to F, clearly I cannot have F connected to C because then I will have a cycle. So C should also be definitely connected to F. And once I do that, then same story here. I cannot have G connected to F, because if I do have that, then GFC will make a V structure which is immoral. So F should definitely go to G. And then I'm done. I have this graph, which is my final class PDAG. All graphs that follow the same structure and arrows here will be I-equivalent, as long as they don't create a new V structure. There is no straightforward way to present the fact that A, B, and BD should not together point to B, because then I will have a V structure. So we just leave it like this. That's the convention. See it in practice. Back to our COVID graph. I'm sure you're all familiar with it. The question is to obtain the class PDAG. Well, first we need to obtain the structure. That's not difficult. We just remove all the arrows, but then we need to keep the immoralities. Here, every V structure is an immorality because, like, there's no covering edge. Look, for example, allergy, congestion, flu. There's no covering edge between allergy and flu. Mask, COVID, social distancing, no link here. So all these ones, like COVID, cough, flu, fever, congestion, allergy, drug, mask, social distancing, COVID, they all are immoralities. So we keep them, but then the other ones we remove. Are we done? No, not yet, because we need to investigate the directions of these blue ones. So for example, look at here. If we have B linked to C, what will happen? I will have a V structure, a new V structure, which is actually an immorality. So I shouldn't do this, therefore C should definitely be linked to B. What about now? Am I done? Well, no, same story. V cannot be linked to B because then VBC will be an immorality. So I should have the direction from B to V. What about here? Is all good? Well, yeah, because if I connect U to S or S to A, an immorality will not be created. A V structure even will not be created because all the existing links here are from flu are outgoing, and same with allergy. So season to allergy will not cause a V structure here. The only point is that I should not connect A to S and U to S so that I cause an immorality. But that we don't present, similar to the previous example. So I'm done here. Okay, to summarize, we asked if there is a class of minimal I maps here. And here, if you look, we had C connected to M, and we had D here separated. Same here, but just M connected to C. And the answer is yes, we can put them together in this class PDAG like this. We just remove the direction, M and C. What does it mean? Well, any factorization of the joint probability distribution that is based on this partially directed acyclic graph, regardless of the directions, M to C or C to M, is a legitimate factorization for our distribution P that is based on this table.